like a nice, intimate presentation here. A presentation about the brain, the amazing human brain. It's incredible when you think about it, right? There's 7 billion people on this planet, and each of us has this little tiny brain about the size of a cantaloupe. And from that symphony of around 80 billion neurons arises thoughts. You have feelings and perception of the world and personality that you eject out into it. From the brain, you can imagine, you can create the fantastic, you can recognize cuteness and ponder why it is that humanity has this ever-growing obsession with cats. You can plot out really detailed experiments, and then you can put them to the test, no matter how insane they may be. And sometimes the action of the human brain might make you wonder, I don't know how we have survived to now. But when you really think about it, of course, the brain is exquisite. It's extraordinary. It's allowed us to image atoms, create governments. There's a freaking whole pod of us living out in space on a station like the size of a football field, and there's a live stream from the space station that you can just watch. It's amazing. And with this organ that we use to ponder our place in this world, we've also started to kind of understand the world itself. Now, you guys probably took Ubers here. This is Amsterdam, so you probably biked, let's be real. If you came from another country, you probably used a really quick website to just, get here nearly instantaneously. But a mere 500 years ago, which sounds like a long time, but in the history of human evolution, that's less than a blink of an eye. This is where we were. This map has coastlines and river deltas, and it also has monsters. Look at this guy. What is this, a pinstripe human thing with a pig butt? I don't even know. From this quest to start mapping our world, we go from mythology to precision, and from precision to accuracy relatively quickly. We begin to chart land and sea and plot harassing air fire, and not just war. We go from mapping the world to understanding the dynamics of the world, which is an interesting step. This may look like a pretty lame, low-res image, but this is a hurricane. This is Hurricane Carla, and this is a radar image from 1961. It was the first hurricane radar image that was ever shown on national television in the United States, and it caused what was the largest storm evacuation ever. 350,000 people fled their homes in Galveston, Texas, because they saw this image of a hurricane. Hey, sorry, we've come a long way in the past few hundred years. You don't even really need to ask about the weather anymore because people are going to tell you about it. Least to mention you can just ask your phone, and if you're in a developed country, you're probably going to get a push notification if anything even remotely dangerous is about to happen. This is to make the point that maps are a foundation, right? They're a scaffolding from which we understand. This connectivity of modern humanity, it's not because of maps, but it's been facilitated in part by it, right? The early maps were flat, they were static, and over time we add layers and layers and layers of complexity. And thanks to modern technology, we add complexity in both space and time, planning incredibly intricate levels of modern society. Now, this is just the connectivity of air traffic in one day, and each one of these little snippets of video is just 1 or 2 hours. It's incredible, and this is just a tiny little piece. Now, a better understanding of the world means that we're in a better position to plan, to forecast, to manage risk. It means that we can ask different questions, because after all, knowledge is really the foundation from which innovation arises. Now, that was air traffic. It looks remarkably similar to the traffic in a completely different world, which is the world of the brain. Now, what you're seeing here along those orange wires, those are fibers of connectivity. So much like there's undersea cables that have lots of little tiny wires within them, the brain has these highways, except those wires are axons. They're electrical cables of neurons themselves. These neurons are clustered and they are bundled together and they go long range for a cell. This is a very, very, very long way until they get to a localized region. So when you see these sparkly things on the outside of the brain here, that's actually different firing frequencies of populations of neurons. But this is pretty low resolution. Now think about it. If you're looking at that air traffic map, right, that shows you people going from A to B, but it doesn't really shine light on the conversations that happen at conferences or over wine or in boardrooms, right? The conversations that catalyze economies that order those flights. At this resolution, we see millions of cells. We don't actually see the individual connections of these neurons. For that, we need to look a lot closer, because those wires end in little groups of cells branching out into arbors that are connected through synapses. Synapses are electrical and chemical junctions through which neurons communicate. They're kind of like, if you were thinking about kind of the language of the brain, these local circuits of neurons are kind of like the words, right? The words that are strung together to form sentences and eventually paragraphs and the stories that underlie our ability to perceive. This is kind of what the brain does. Now, in order to map the brain at that resolution of synapse level resolution, neuroscience doesn't typically look like these beautiful, accurate visualizations that you're seeing. Neuroscience, in this case, is more a big data problem. We build sophisticated software that tries to analyze this data. So we image the brain at nanoscale resolution, trying to chart out one or hundreds and thousands of the 100 trillion some odd synapses that are found in just one single brain. And it's incredibly difficult. It's incredibly time-consuming. It's a big data problem. I would argue that the biggest hurdle neuroscientists face today is just analyzing their data. And so what we do, the way that we started, was we build AI. We use deep learning to automatically segment out the data sets. So to try to automatically decipher one neuron from another within our data set. And I know that as soon as you start saying neuroscience and AI in a presentation, these like horrific Hollywood memories start popping up. But just a reminder of like where we are. It's like so close. But so far, I think Tesla put this greatly, right? That it's relatively easy to build an AI that's 99% accurate, but it's vastly difficult to build an AI that's 99.999% accurate. And that's ultimately where we need to be. Now, the challenge, this may seem like a tiny change, but when you're dealing with a big data set, a tiny fraction of error amounts to a huge amount of human time required to fix that error. That's the fundamental problem of AI and automation. In neuroscience, for example, that tiny bit of error, it amounts to dozens of hours to reconstruct one neuron, dozens of hours of expert time. Labs just don't have that. And so while on the one side we are working to build much better software, it's not going to happen overnight. We need to make discoveries now. We need to understand how the brain does what it does so that we can fix it when things go wrong. And so this kind of got us thinking, right? I mean, our problem right now is that we need time. Our software kind of looks like fitting little Legos together. It's kind of like this little 3D puzzle of sorts. Where can we find people who have time to play puzzles, like gamers? And this was the eureka moment for us, where we wondered, could we turn our lab software into a game? Now, this is not a novel idea, right? People have been playing games for thousands of years. And, think of this. This is running. They turned running into a game. And increasingly more elements of modern society are gamified. Now, you don't typically think of Facebook as gamified. There's not really a leaderboard. There's just a news feed, which is basically a leaderboard. You don't get a score, but you do get likes and comments and reactions. You don't get a score from Uber, but you definitely leave a review at the end. These elements of game design make the world more engaging. They trigger natural circuitry in the brain so that every time you check in, you're getting a little hit of dopamine that makes you check back more, post more. So we used all this to inspire the design of EyeWire. which is a pilot project that began at MIT. It's quite literally a game to map the brain. So we launched this pilot in 2012. We weren't sure if it would work. Most people were very vocal in telling us that it would not. However, a few years later, we have 250,000 players from 150 different countries who do this. So this is just a really brief snapshot of the game itself. That blue thing in the middle, that's an individual neuron. The players have mapped hundreds in the game. There's live chat, and at any given time, there's 50 to 100 people online. We have a robust stats panel and a badge system for the players. So when you go in and actually hit start playing, it zooms you into a tiny cube, which is a little volume of brain. And that blue thing that you're seeing, that's a branch of a neuron. And what actually we're trying to do here is click and add these pieces to map the branch from one side of the cube to the other. Now, neurons are natural, they're biological, they're smooth, they do not have jagged edges or sharp edges. So what the gamers learn to do is look for flat edges, and when you click, it adds a 3D chunk. Now that 3D chunk, that's what our AI has done. It automatically generates all these little pieces, but it can't fit the pieces together into a complete whole. That's what the human has to do. So once you've found all the pieces in the individual cube, you kind of give it a quick look over, make sure that nothing's missing. You hit submit, you get points, and then you move on. Now, there's a lot of kind of difficult cubes, and there are lots of different modes of play. As players kind of advance within the ecosystem, they kind of level up. We have chatbots, we have robust API, so players have built their own browser plugins that allow the top ranks of the EyeWire player base to kind of interact with the game. And as you kind of get better and better at the game, you start moving from interacting within the cube to interacting within the cell as a whole. So in a way, we are kind of crowdsourcing the accuracy of our crowdsourcing system from amongst the top players within our game. It's great, and it's working really well. We've published several papers. We also do all sorts of kind of fun competitions, zombies versus vampires, tyrannosaurs versus velociraptors, because this is serious neuroscience. And it's a game, And I think the idea that this is a game really epitomizes what we're trying to do and what we stand for, right? That for most of the history of science, science itself has been kind of locked away, right? Around the same era as that early map that you guys saw, the word scientist didn't even exist. It was literally something for aristocracy that noblemen did for fun in their spare time. Then as science emerged and evolved, it became locked behind lab doors. And if you did not choose to do science as a career, you had basically no chance of getting into it. But now with projects like EyeWire and other citizen science endeavors, anybody, anywhere with an internet connection can help. Now this is transformative. This is revolutionary because this is at the front lines of neuroscience. And as people play, they learn. It's not an educational game, but they just learn. We do all sorts of studies, and this kind of shows they learn terminology, they learn connectivity, they learn anatomy, and they learn how this intricate network of cells creates a human being, right? And that's really what we're trying to figure out, is how a physical brain creates a cognitive mind. It's one of the questions that has kind of risen in human minds ever since we've been able to call ourselves human, right? And probably at conferences like this, lots of people wonder, like, how did you think of that? Or where did that idea come from? Or do you ever wonder when you have a new idea for a new project or a new company, like, where did that emerge? Those are the kind of questions that fuel me. And before I got involved in this project with EyeWire, I found that those answers were very far away. But I think by crowdsourcing and by engaging the general public, it presents a completely different approach to solving these most difficult challenges. It's no longer only the brains of researchers who are trying to figure them out. Now it's anyone who has an interest, anyone who's a hacker, anyone who's a puzzle solver, a designer, people who are bringing their different perspectives to the world of neuroscience as a whole. And wouldn't it be something if the key to all that was gamers? Thank you.